Hi everyone, this is a work done by me, Tarcísio Deda, and the Professor William Wolff, both from the University of Campinas. In this work, we present the application of extremal seeking control, or simply ESC, on the reduction of noise produced by an airfoil. Nowadays, flow control finds applications in different engineering problems, such as mix enhancement, lift improvement, drag reduction, acoustic noise reduction or suppression, which is the case we study in this work, transition delay, and separation delay. So, why use control? In general lines, we can think of control as making interventions to a given plant in order to stabilize a naturally unstable system, achieve some project performance requirement, make some functionality robust to unexpected phenomena, to make some variable follow a reference command, and to allow for online optimization of some variable in real time. Here, I point some differences between open-loop and closed-loop control systems. Basically, the measurement of variables of interest in closed-loop approaches gives information about how far your system is from a desired operating condition. Open-loop control is usually applied when your system has a predictable behavior and you can use constant or time-based interventions. A group of flow control approaches can be classified as passive control, which usually consists in adding riblets or other geometric assets and taking advantage of certain material properties. In this class of control systems, there is no power consumption involved. As opposed to passive control, active control uses some source of power to enable more adaptable configurations. Some of the main categories of actuators are fluidic actuators like mini-jets, moving surfaces like active flaps, and plasma actuators. Our control application is implemented in a high-fidelity numerical solver for a NACA0012 airfoil. A pair of grids is used, one near the wall, represented in black, and the complementary one represented in red. The inner mesh is solved using an implicit beam and warming method, while the outer one uses a Runge-Kutta scheme. We use two different sets of grids for different Reynolds numbers. The lower Reynolds case is shown at the upper figure, while the animation at the bottom figure shows the mesh for the higher value case. Both cases studied are for Mach 0.3 and a 3-degree angle of attack. The Reynolds numbers chosen for each one are 10,000, at which the flow develops a von Karman vortex street, and 100,000, where Thomas-Schlicht instabilities produce structures along the suction side. Here, I'll give a brief explanation on how extremum seeking control works. The goal is to find an optimal control input U that minimizes or maximizes some property of interest. First, we guess an initial value for U and apply a periodic perturbation to the system. At the output, we evaluate some cost function to see how the system responds. If the choice of omega obeys some timescale restrictions, we can expect the cost function to respond with the same frequency. If the input is not optimal, an increment to it shall result in increasing or decreasing the cost function. Phase delay may occur, and for the system we are studying, we don't know its value since it can change for different values of U. We can take the response, shown in black, and apply high-pass filtering to end up with a wave that oscillates around zero. The filter can add a lot of phase delay, but the amount is known since the filter is linear and we can compute phasing for each frequency. We now use a matching synthetic wave to compare to the filtered cost function. This new synthetic wave, shown in dashed blue, has the same frequency omega and has its phase compensated, resulting in the solid blue curve. We then multiply both waves represented in solid lines. Let's see what happens. The result gives us a wave that is mostly either positive or negative. We can then filter it to reduce ripple. A positive or negative function indicates the way we must change the input to move towards the optimal. The resulting loop looks like this. We apply the disturbance, evaluate the cost function, high-pass filter the cost, multiply to a synthetic wave, reduce ripple with a low-pass filter, integrate the result to obtain a new value for the input to be summed to the perturbation in the next iteration, and then the loop's closed. We can use ESC when we need to find an optimal input. In cases where the function presents a plateau, we can add a compensation to drift the equilibrium derivative from 0. In our setup, we use a cost function that depends on the pressure fluctuations, since we aim to minimize noise. The measurements are made 1 card above the leading edge at the red X mark. The actuators are suction or blowing devices. The momentum values are weighted on the grid cells according to a position, a maximum intensity, and a cosine window function. For the simulation with Reynolds 10,000, we guess initial position for the actuation at different points, indicated by the pink mark. In the upper case, we start at 82% of the card, near the trailing edge, while the other case uses an initial guess at 20%, near the leading edge. The ESC loop searches for the optimal position for noise reduction, and is able to find it in both cases. Here, a weak amplitude of suction is logged, only the position changes. With a stronger fixed intensity, there is a region near the center where the flow reattaches, becoming stable and suppressing the vortex street, the only mechanism of noise generation for this Reynolds number. Let's hear the simulation. Here we can see the divergence of velocity and the pressure fluctuations where there is no control with weak optimal actuation and with strong optimal actuation. The noise presented in the higher Reynolds case has components in a broad range of frequencies, as opposed to the lower Reynolds case, which basically produces a tonal noise. For this problem, we use a combination of ESC to find a position for an actuator and slope-seeking control to find an intensity for another one. Let's see it in a video. Here are some snapshots of the Reynolds 100,000 case. This is much less organized than the Reynolds 10,000 case. We can see the formation of coherent structures at the suction side. That's the position where we take measurements, and that's the initial position guess for the actuator. The ESC loop perturbs the actuator around its central position. The integration pushes the actuator towards the center of the airfoil. We can compare two cases with two different initial guesses. Notice how the instabilities disappear at the suction side. That's cool, isn't it? The actuators stop when an optimal region is reached. The perturbation remains though. Now the vortex street is the only mechanism that produces noise. With the suction side actuator, it looks much more like the Reynolds 10,000 case. It's organized and periodic. Now we put a new actuator right at the trailing edge, with the position locked, while the previous one is still at the optimal location. By using slope-seeking control, we can find a quasi-optimal suction or blowing intensity to suppress noise. That bar indicates the intensity. Notice that for higher blowing values, the oscillation amplitude at the street decreases. The slope-seeking compensation does not let the amplitude grow indefinitely. But if it would, that's what we would see after a critical point. Everything is steady and stable. Now let the measurements shine. Some of the final thoughts I can bring are: solving optimization problems online can be a feasible alternative to robustly controlled systems with complex dynamics. ESC and slope-seeking were able to reduce or suppress noise in different configurations. High-fidelity simulations are expensive, but we are looking forward to use reliable, reduced-order models to attenuate control design overheads. Finally, we thank FOPESP for funding our research and making this work possible.